previous video, we looked at some of the logic behind functions and their limits as x approaches infinity. And from that, we can derive a generalized rule for rational expressions of polynomial functions. We established, for instance, that the highest power in the function is going to be the one that dictates the direction of the function, and that makes sense because as our inputs, our x values, get larger, then the highest power of x is going to be what determines the direction of the function because it's going to get larger faster. So then, if we have f of x over g of x, a rational function, if the higher power is in the denominator, then we can conclude that the denominator is going to get larger faster. As a consequence, the fraction itself is going to get smaller, and we're going to approach 0. If the higher power is in the numerator, the opposite happens. The numerator gets larger faster, at an exponentially larger rate, and therefore, we're going to approach a larger and larger value with no boundary, so infinity. Now, it is important to note, this may be positive or negative infinity. And that depends on the specific signs, as well as whether we're approaching positive infinity or negative infinity, and the powers. We're going to discuss that in a separate clip altogether. Finally, if the highest powers are the same, then what we're going to do is we're going to take the ratio of the leading coefficients and simply put them over each other and get a over b as our limit. So let's take a look at a couple of examples. Let's start with number 1, which we've already established from before. There is no denominator here. Everything is positive. We're going to positive infinity. Let's deal with just the highest power. This is basically a parabolic function. So as x gets large, this is just going to get large, and this is going to get slightly less large, and whatever. We don't have to divide by anything, so we know this is just infinity. The second one is a little bit trickier, and we're going to take two different approaches to number 2. The first approach is to try to think it through logically. What happens if I put a larger number in for x here? Well, I'm going to get 5 over x is just going to get closer and closer to 0. So then we can conclude that this function essentially is going to behave the same way as x squared is. And thus, the answer here is also going to be infinity, just like the first one. Now, if we want to take it from the rational function perspective, we can do that as well. We've got x plus 5 over x squared, meaning times itself. Let's FOIL that out. And we're going to get x squared plus 5, that's 5 over x times x, plus 25 over x squared. Now we know, and we can rewrite this as plus 10, we know that the highest power here is this x squared, but for consistency's sake, let's actually get this to be a full rational function with just one numerator and one denominator. So I'm going to multiply both the first two terms by x squared over x squared so I can get this all into one cohesive fraction. And what we're going to get is we're going to get x to the 4th plus 10x squared plus 25 all over x squared. So I've got all the terms have a common denominator, and now I've combined them. Now we see that the higher power here is in the numerator than in the denominator. And since these are the only two terms that end up mattering, we know conclusively that this is going to be infinity as x gets very large. Number 3, we've got the same maximum power in the top and the bottom. They're both 1. So again, we can ignore the 1 and the 8 here. They're going to become less significant. We're only dealing with the highest powers. And here we're going to take the coefficients of the highest powers, which are -4 and a de facto 1. And our answer here is just going to be -4. The fourth question, same thing. Highest power is here and here, x squared and x squared. The lower power terms end up being insignificant as x gets very large, so we are going to approach 6 over 2, or 3. Now this last one, number 5, a little bit tricky. In number 5, it appears as though we have the same highest power, but we actually don't, because the numerator here is under a square root. So let's reduce this to just the highest powers. So we have rad 4y squared over y squared. We can neglect the lower powers, again, because as the y gets very, very large, they're not going to affect our output all that much. So then, the square root of 4y squared is actually 2y, and now our higher power is actually in the denominator, where here the power is 1, so this is going to approach